In this example, we're going to calculate the volume when we rotate a region about some axes. I'm going to use the y-axis on this one, so we'll rotate about the y-axis. So as we look at this one, I'm going to make first a statement will rotate about the y-axis. And I like to draw that picture. Whether we're using the disk method, washer method, it's the same thing essentially. Or in this case, the shell method, showing where that radius goes to is very important. So whatever radius that I want to talk about needs to now go to the y-axis because I'm going to rotate about the y-axis. I have a region that's going to be bounded by this function f of x, which is this right here. F of x is square root of x. So I've made a note of that. I'm also going to give a boundary of x equals 4. And so I'm going to draw a vertical line here at x equals 4, and then y equals 0, which is our x-axis. So I'll just sketch those in. Making a little image is very helpful in a case like this. There we go. Here's our x equals 4, and our y equals 0 is right here. Y equals 0, also known as our x-axis. So we have this region, and I'm just going to highlight it. This is the region that I want to show in this example. And this region will be rotated about this y-axis. We're going to use the shell method to calculate the volume. So when we use the shell method, it's very helpful to draw a representative element in here. I'm going to draw the thickness of the shell that I'm looking at some x value in here. I can pick anywhere I want. It looks like it'll fit right in here nicely. There's my x value, and here's the thickness of the shell. So this shell, well, it's going to look like this. I'm going to make a little picture here so I can talk about the shell, this one shell. And so I'm going to show what this thing looks like as it's rotated about this y-axis. I picked x equals 2 here, which is about 1.4. 1.4, right about there. And it looks like this. Well, it keeps going because I'm going to go all the way to x equals 4. And so the square root of 4 is 2, so it looks like we end up at 2 over here. I'm just going to try to sketch this. It doesn't have to be all that perfect, but here is the shells where they live. I'm going to draw this other part of the shell right in here. It says this thing's rotated around. You could see this one shell. Let me just try to make a picture that's reasonable of this shell. There we go. Looks like this. I probably should have made this one a dashed line because you can't really see it from this angle that I'm illustrating it. So I'll just kind of ghost it out like that. There's our shell, but you would be able to see this top part here. So I'm going to draw that like this. There we go. So here's one shell. Now what I'd like to do is I'd like to make something so we can really see this. What I've got shown here is a radius. And x is going to define our radius because our radius is always drawn to this axis of rotation, just like the spokes of your bike are attached to the hub. You think of this as the hub. So here's x defines the radius. The specific example I drew is when x equals 2, so the height of this shell, height, is defined by the function. So we can see the radius is defined by x and the height is defined by the function, which in this example is the square root of x. So we have both the height and the radius, but what I would like to do is I'd like to see an actual shell. So I'm going to take a piece of paper and I'm going to say when x is equal to 2, so I can draw this same shell that so I can create this same shell that I've drawn. I'm going to show this height here of 1.414. That's the square root of 2. And so this shell, as I talk about the circumference of the shell, we know it's a circle, and the circumference of a circle is the pi times diameter, or 2 times r times pi, or 2 pi r, well, pi times 2 times another 2 is 4 times pi. It's a little more than 12 and a half. You can grab your calculator, and a little more than 12 and a half. So what I'm going to do is I'm going to find a little more than 12 and a half, and I'm just going to mark it off using the scale here, so that when I cut this out, I'm going to grab a scissor and I'm going to cut this out, and then I'll have a shell that we can actually look at. So here it is. Here's the shell. And it's actually just a rectangular piece of paper right now, but it's, well, when we think of the thickness of it though, remember the thickness of this shell I drew in here, that's the thickness of this paper as I have this representative element. So I think what I'm going to do is, I've got the radius described, the height described of this one shell. I'm going to talk about the thickness of that shell, and it's in the x direction, so I'll just put a little delta x like that. So the width of this piece of paper then we'll just say is delta x. So now as I talk about the volume of this, well, the shell, when it's in this stretched out form, it's just a rectangular prism. This length here is the circumference, and the height here is given to us as our function. The radius is x, so the circumference then would be 2 pi times x. That's our circumference. The height then is going to be the square root of x. Square root of x. So there I have the height and the circumference, or length, of this rectangle. And remember, the thickness is that delta x. So if I want to talk about the volume of one of these shells, let me just hold it together like this. There's our shell. All I have to do is multiply 2 pi x times the square root of x times delta x, and I'll have the volume of one shell. So let me make a note of that. Volume of one shell. I'll just put a little delta volume because I'm talking about just that one shell. Is our circumference 2 pi x times the height, square root of x, times the thickness, delta x. So this representative element, that one shell that we drew, really helps us see our formula that we'll use when we're using our calculus techniques of integration to find the volume of this region rotated about the y-axis. So it's a delta x problem. I've got the volume of one shell. Let's talk about the volume of infinitely many. So we're going to integrate 2 pi x square root of x dx, now I want the infinitely many shells, from 0, x equals 0, over to x equals 4, that highlighted region. And that'll give us the total volume. As we evaluate the definite integral, 2 pi is a constant, so I'll just put that out front. X to the 1 times x to the 1/2 is x to the 3/2, so the integrand is x to the 3/2, and then I have my differential dx. So all we have to do is find an antiderivative of x to the 3/2. This, of course, is super easy for us, so we'll be able to use the fundamental theorem of calculus for this one and evaluate it. So I'll do that. Alright, so I found the volume. Just going to highlight this. This is our volume that we found. That would be in units cubed. I think what I'll do is I'll grab my calculator and I'll give an approximation to this using my calculator feature. So to do that, what we might like to do first is put the integrand the x to the 3/2 power in our calculator like this. Ooh, no, not quite like that. Let me fix that. There we go. So I've just typed in x to the 3/2 power, this part right here. And so I'll leave then, second quit, and I'll go to my home screen, and I'm going to type in 2 pi, and then I'll call up my function integrate, number 9, under the math menu. The limits of integration 0 and 4. Integrand was here in y1. Green button F4 is a little shortcut button. Now the advantage of doing it this way is just a little bit neater, quicker, and then I have a decimal approximation. And so if 128/5 pi is about 80.4247, then we've got some numerical support. So I'm going to see if that's actually true. Yep, looks like we got some numerical support for this. Now just an FYI, this volume could have been found using the washer method too. We'd, if we made our washers in this case, they would still have to be drawn to this axis of rotation. The height of those washers then would make it a dy problem. But you'll get the same volume. What do we have for an approximation? 80.425 units cubed. There we go, something like that. I like to give a decimal approximation along with the exact answer. Just would like to get a little numerical support. But I usually am not done yet. Somewhere in here I like to have a picture, and sometimes I draw the picture right away, sometimes I draw it at the end. But I like to draw the picture of what this thing actually looks like, and I invite you to do the picture also. You know, as you draw this out, here it is. This is our three-dimensional shape here. I'm just going to highlight the whole thing, and I like to imagine, you know, what does it look like? Like this part right here you wouldn't really see. You'd see this part here. It looks like one of those things that you drop a coin into and they spin around and around and around and down they go.